Okay, so this was where we stopped last time. So in the last video, we talked about the hash function. So the fundamental idea of the hash function is even though we know, well, the universe of the possible keys is very large. However, we only want to maintain a reasonably small hash table T. So in this case, the university of the universe of the keys U is very large. However, the size of the table M is very small. In this case, we have to map the keys to the possible slots in the hash table, and collision may happen. The reason is there are more possible keys than the available slots, so eventually we will have collisions. That's guaranteed. So for this one, if we have the key 5 and the key 2 and there are two keys, and if we send both the key 2 and the key 5 to the hash function, and we assume that the hash function is h, okay, so hk2. So h is a hash function and the k2 is a parameter. So hk2 equals hk5, and then we will have a collision because after applying the hash function, both key 5 and key 2 will be mapped to the same slot. So the next question is, how are we going to resolve the collisions? So there are two possible ways. The first way is called chaining, and the second one is called open addressing. So this is the term in our textbook, and you may have seen another term called probing. Okay, so let's talk about the open addressing or the probing first. So the idea is if we want to use a specific slot because the hash function maps me to that slot. However, when I visit and see that slot, this slot has already been taken. After that, what I can do is I'm gonna keep on moving down using a specific strategy until I find a open slot, and then I will take that slot. Okay, so this is the idea called probing. So for the probing, one of the problem is, well, if we want to delete a record from the hash table, this could be a problem because this one, the record is here probably because of the probing strategy applied. So when we delete that, and it may break some of the later probings or the later searches. So it doesn't work very well. Well, there are tricky ways that you can make it work, but usually people will use the probing strategy or the open addressing strategy when you have a fixed set of data and you want to put that into a hash table. So, or you want to have a collection of the data. You will add more things, but you don't think you're ever gonna delete the items from the hash table. So number one, if you have a fixed set. Number two, you're having a increasing set, but you don't have to delete anything. In those two cases, you can definitely use open addressing or probing. And an example is if you want to build a spell checker. And in this spell checker, you want to keep all the valid English words into a hash table. This is big hash table, right? Even though it is a big. Number one, well, probably at the very beginning when you build this hash table, you have already decided all the valid English words. So that's the case one. And another case might be later, you may want to add a few more new words into your valid English words hash table. However, you are adding new things, but you are not taking anything out. So in those two cases, well, you can definitely try the open addressing, and it works well. So another solution is called chaining, and for the chaining, it means for each of the possible slots, we know there will be collisions. However, when collision to prevent the collision to happen, we allow the different keys to share one slot. So how can we do that? We can, for each of the slots, we just create a linked list. So it should be like this. So for example, for this slot, it is instead of holding one value, we treat that as the head of a linked list. So you can see key 1 and key 4, they share the same slot after mapping the after being sent to the hash function. So in this case, they will share this slot, and well, since it is a linked list, so we will have the K1 as the first node and K4 as the second node. So in this case, is there a collision? Yes, it is on this slot. However, since we create the linked list, so we are fine in this case. So if we are doing the chaining, and it will change our strategy on insertion. So if we want to insert an element, and the strategy will be, if we have the K10, for example, and K10 is mapped to this slot. So how can we do that? This slot itself is empty for now. So we have to initialize a linked list, and then we want to put the K10 here because that is the first node of the corresponding linked list. So another possibility is if we want to insert to a slot where there is already a linked list. So for example, we have K12, and K12 will map to this linked list. So in this case, K12 will be the last node here, or probably it makes more sense if you want to put the K12 here. Okay, so this is the way that we can insert one node to the hash table. And how about deletion? So if we want to delete a node, and well, it is equivalent to how we are going to delete a node from a linked list, right? So if we want to delete the K4, and then we will say K1's next reference will point to none. So to delete a key and the corresponding value, in this case, we are just gonna delete the corresponding node in the linked list. So the next question, do we need a doubly linked list for efficient delete? So you really need to understand, or you really need to review, how do we do the deletion in the singly linked list and the doubly linked list. So let me help you review the single linked list first. So for the single linked list, we have the head, and then we point to one node and then another node. Okay, so in this case, if we want to delete a node, so for example, we want to delete this one. Okay, in this case, we should know the node we want to delete. However, remember, we also need to know the predecessor, right? So in this case, when we set up the search, before we do the deletion, we want to use two cursors. One cursor, we can call that the current. So this is the node we want to delete, and we also want to use another cursor called previous. And eventually, what we have to do is we want to do previous dot next equals current dot next. So we are gonna skip the current node by pointing the previous next to the next node after the current, if there is one. So in this case, if it is already none, and we are pointing the next reference of the previous to the none in this case, so this node is really deleted. Okay, so this is how we can do the deletion with the single linked list. And the next example, how do we do the deletion for the doubly linked list? So for the doubly linked list, we have the head, and then it points to one node, and it will point to another. And let me just do one more. Okay, so this one is the reference to the next, this is the reference to the next, and we will also have the reference to the previous, the reference to the previous. Okay, so in this case, if we want to delete this node, and what are you going to do? So you are going to find the previous next. So previous next will point to the successor, and the successor's previous will point to the predecessor. So this node is eventually, okay, so this node will be deleted. So the predecessor's previous, oh, sorry, the predecessor's next will point to the successor. The successor's previous will point to the predecessor. So in this case, no matter if we are doing the single linked list or the double linked list, well, the cost of the deletion are actually the same. Okay, so with that being said, let's come back to this question. So do we need a double linked list for efficient deletion? Okay, so in this case, no matter we are doing the single linked list or double linked list, the cost of the deletion will be the same. Well, it doesn't hurt anything for us to use double linked list, but using double linked list won't improve anything. So that's the point. So how do we do a search? So if you want to do a search, what we have to do is we have to take the key we are searching for, and then we have to apply the hash function. So if after it applies the hash function, and then it points me to this linked list, and then this linked list hasn't even been started yet. So I can say, okay, I look at that slot, and that slot itself is empty. There's even no linked list there, so I can't find this value. Okay, and another possibility is it points me to one of the linked lists, and this linked list is already there. So in this case, I do have to do a linear search in that linked list. So I have to visit all the nodes in the linked list in order to find the value I'm looking for. Okay, so this is for the search. So I guess that's it for today's lecture.